Have you ever heard phrases like, "time is running out," or "I don't have enough time," in your busy daily life? What is time, really? Is it the rising and setting of the sun, or merely the ticking of a clock? Most of us believe that time is something simple. It flows steadily from the past to the future, can be measured, and always exists. But what if I told you that our understanding of time is merely an illusion, a creation of human perception? Would you believe it? Join World Mysteries as we unravel this intriguing enigma. If you're fascinated by stories that challenge your understanding of reality, don't forget to hit like, share, and subscribe to our channel to never miss out on our exciting content. Aristotle, the first to ask the question, "What is time?" left behind a revolutionary perspective in the history of philosophy and science. As a renowned philosopher and scientist of ancient Greece, he defined time in his work Physics as the measurement of change. For instance, if you leave your house in the morning and return after 2 hours, those 2 hours serve as a measure of the change between leaving and coming back. But here's the intriguing part. If nothing moves or changes, does time cease to exist? If Aristotle were here to answer, he would say that in such a case, time does not exist. However, if that's true, why is it that when you lie still in the darkness, preparing to sleep, you can still sense time passing? Aristotle addressed this in Physics, explaining that even when everything outside seems still, there are thoughts and movements within the mind. These inner changes allow us to perceive the passage of time. In other words, while the external world might appear motionless, the changes in our thoughts and emotions are also a form of movement. Without motion, there would be no time, because time is merely a record of change. At first glance, Aristotle's theory might seem peculiar, especially if you're more familiar with Isaac Newton's perspective on time. To better understand, let's delve into Newton's viewpoint in the next section. Absolute or relative time? Isaac Newton, one of the founders of modern natural science and celebrated as the father of modern physics, proposed the idea of absolute time. He believed that a true, universal time exists independently of any changes in the physical world. Even if all objects were motionless, or even if the activity of our minds came to a halt, this absolute time would continue to flow steadily, unaffected by any external factors. While many consider Newton's idea of time as uniform and independent to be common sense, it wasn't a concept ingrained in human intuition from ancient times. In fact, most philosophers throughout history have not fully agreed with Newton's perspective. For centuries, people found themselves caught between the towering ideas of Aristotle and Newton, debating whose vision of time represented the truth. Then, Albert Einstein, a revolutionary figure in science, introduced a groundbreaking theory that reshaped our understanding, the theory of relativity. Einstein declared that time itself is an illusion and that the human distinction between past, present, and future is ultimately a misconception. But before diving deeper into Einstein's ideas, let's unravel a perplexing question that has puzzled physicists for decades: the constancy of the speed of light, often referred to as invariant velocity. What does this mean? Traditionally, we understand speed as relative. For example, if someone is on a train moving at 50 meters per second and they throw a ball at 3 meters per second, from the perspective of someone on the train, the ball's speed is 3 meters per second. However, to an observer on the platform, the ball's speed would appear to combine with the train's, resulting in 53 meters per second. Logically, one might assume the speed of light behaves similarly. Yet in 1887, an experiment conducted by two American physicists, Michelson and Morley, shocked the scientific world. This experiment, later known as the Michelson-Morley experiment, revealed that regardless of whether the Earth's motion was aligned or opposed to the direction of light's travel, the measured speed of light remained constant. This finding implied that if the ball in the train example were replaced with a photon of light, both the observer on the train and the one on the platform would measure the photon's speed as identical. The Michelson-Morley experiment was repeated over decades, with varying environments and conditions, but the conclusions remained unchanged. How could this be? How can something so fundamental defy the traditional laws of motion? Einstein's revolutionary insights would eventually provide the answers, but not without rewriting the very fabric of our understanding of time and space. Time, a miraculous transformation. Finally, the mystery of time comes to Albert Einstein for an answer. He asserted that absolute time does not exist, nor does absolute space. Instead, Einstein proposed a revolutionary concept, the unification of spacetime. This means we cannot discuss time or space in isolation. Instead, we must view them as a single, intertwined entity, spacetime. Like temperature fields or electromagnetic fields, physicists refer to spacetime as a gravitational field. This gravitational field, like everything else in the universe, is not absolute, uniform, or fixed. It can bend, stretch, and interact with other fields. At times, the gravitational field may appear flat, as described by Newton, but it can also oscillate, producing what we know as gravitational waves. These oscillations are what cause the transformation of time, providing an explanation for the phenomenon of invariant light speed. So, does this transformation of time follow any rules? To understand, we turn to Einstein's theory of relativity, which consists of two parts: special relativity and general relativity. According to special relativity, time passes more slowly for objects moving at high speeds compared to those at rest. General relativity, on the other hand, shows that time is also affected by gravitational fields. Specifically, time for an object in a stronger gravitational field passes more slowly than time for an object in a weaker gravitational field. This means that time at your head passes faster than at your feet, simply because your head is slightly farther from the Earth's gravitational field than your feet. Based on this principle, an intriguing hypothesis has emerged. Standing upside down could help you age more slowly. Could this really be true? And has Albert Einstein truly unraveled the mysteries of time? Let's explore some classic and fascinating examples together. The atomic clock experiment, a vivid demonstration of relativity. In 1971, scientists Joseph Carl Haffel and Richard E. Keating conducted a groundbreaking experiment using cesium beam atomic clocks, renowned for their unparalleled precision. For instance, an atomic clock in Germany has a time deviation of less than 1 second over 187 million years, making it an ideal tool to test whether time truly transforms. In their experiment, Haffel and Keating placed two atomic clocks on two commercial airplanes flying in opposite directions, one eastward and the other westward. The reasoning behind this setup was that the eastward flying plane, moving in the same direction as Earth's rotation, would have a higher relative velocity. Conversely, the westward flying plane, moving against Earth's rotation, would have a lower relative velocity. This speed difference between the two planes would amplify the results of the experiment. Moreover, the atomic clocks on the planes were at higher altitudes and moving faster than the clock placed at the U.S. Naval Observatory, which remained stationary on the ground. These differences in altitude and velocity allowed the experiment to test both special relativity and general relativity. According to special relativity, time on a faster-moving object passes more slowly. Meanwhile, general relativity posits that time passes more quickly in regions with weaker gravitational fields, such as higher altitudes. The results of the experiment aligned perfectly with Einstein's predictions. The atomic clock on the eastward flying plane, faster speed, lagged by 59 nanoseconds compared to the clock on the ground, while the clock on the westward flying plane, slower speed, gained 273 nanoseconds. These findings not only validated Einstein's theories but also have practical applications in modern technology. The GPS systems we rely on daily require time corrections based on relativity. Without these adjustments, atomic clocks on satellites, operating in weaker gravitational fields and moving at high speeds, would run 38 microseconds faster than clocks on the ground each day. While this might seem like a negligible amount, consider that GPS systems require time precision at the nanosecond level. A 38 microsecond discrepancy, equivalent to 38,000 nanoseconds, could accumulate to a positioning error of up to 10 kilometers per day, an unacceptable margin for accurate navigation. NASA's Twin Experiment, a fascinating glimpse into time and space. In 2015, NASA conducted a unique biological experiment involving identical twin astronauts Scott Kelly and Mark Kelly, who share the same genetic makeup. For this experiment, Scott was sent to the International Space Station, ISS, to live there for 340 days, while Mark remained on Earth. Upon Scott's return, scientists compared genetic changes between the two to study the effects of space travel on the human body. Looking at photos released by NASA, do you think Scott, who lived in space and traveled at high speeds around Earth, appeared younger? Although no pre-experiment photos were made available for comparison, NASA's findings revealed a remarkable outcome. Scott aged more slowly than his brother Mark. But what exactly happened? When analyzing Scott's genetics, NASA discovered that during his time in space, his aging process significantly slowed. Specifically, the telomeres, small DNA segments at the ends of chromosomes that protect them from damage, in Scott's cells shortened at a much slower rate than those in Mark's cells on Earth. Typically, as humans age, telomeres gradually shorten, leading to cellular aging. However, in space, Scott's telomeres exhibited a reduced rate of shortening. Interestingly, upon his return to Earth, the rate of telomere shortening quickly reverted to normal. The ancient saying, "one day in the heavens equals 1,000 years on Earth," suddenly seems to hold more weight. Inspired by Einstein's theory of relativity, in 2015, MIT philosopher Bradford Skow developed the block universe theory. According to this theory, time and space are inseparable entities, part of a four-dimensional universe consisting of three spatial dimensions and one time dimension. Rather than viewing time as a continuous flow, as we typically perceive it, the block universe theory suggests that time is a static dimension within spacetime. We only perceive the present because we are entities moving through spacetime. Every moment in time corresponds to a three-dimensional snapshot of the universe at that specific instance, and the entire block universe is made up of an infinite collection of these snapshots. Imagine if we could step outside and observe the block universe from an external perspective. It would be like watching a movie. You could pick any point in time to view what happened at that moment. Just as pressing the play button on a movie causes it to unfold, time in the block universe progresses continuously as we experience it. But why do we perceive time as flowing from the past to the future? Physicist and philosopher Max Tegmark from MIT, along with physicist Julian Barber, believes the switch lies within our brains. They argue that the passage of time is merely an illusion created by the brain. The neural structure of our brain allows us to retain memories of the past but prevents us from knowing the future. This creates the impression that time flows. It's this mental process that gives us the sense of time moving from the past through the present, and then into the future. What about you? Do you think time is truly flowing as we perceive it, or is it merely an illusion? Share your thoughts in the comments below. We'd love to hear your perspective and discuss it with everyone. Don't forget to hit like, share, and subscribe to World Mysteries to continue exploring the universe's greatest enigmas with us. Thank you for watching until the end, and we'll be back with more fascinating stories. Goodbye for now, and see you on our next journey.